In the following video, I will present the publication titled Robust Visual Servoing under Human Supervision for Assembly Task, submitted to the European Control Conference 2025. This work is associated to the Digital Futures Smart Construction project. The aim of this work is to use omnidirectional mobile bases equipped with 6 degrees of freedom manipulators and RGB depth cameras to pick and stack blocks to assemble different structures. We are particularly interested on creating a set of pick and place actions that can be used with higher level planners and that can achieve our goal while ensuring object visibility is never lost. To do this, we design a quadratic program that takes the end effector twist values provided by an independent visual servoing controller and several control array function constraints that efficiently adapt the end effector speed to ensure visibility. The visual servoing controller goal is to bring the end effector to the desired location in front of the assembly blocks and can also receive human commands inputted through a joystick. The barrier conditions to ensure visibility are created using the position of the 4 corners of Aruco markers taped in each face of the blocks. If these corners are inside of the field of view of the camera, which we describe as a visibility volume, then the barrier condition H will be greater than 0 and visibility is ensured. These constraints are transformed to depend on the control input of our system, which is the twist of the end effector, and by solving the QP problem, we obtain a final control command to send to the manipulator. In the left, we saw the basic visual servoing implementation without our CVFs, and in the right, we saw one with them. As we can see, when the CVFs are active, we can ensure full visibility of all marker corners. Next, we bring this controller into a roster architecture to create the picking action. The camera publishes an image that is then used by OpenCV to track the object. This is then passed to our controller to obtain a final twist, which is then converted into end effector motion with a servo node from Movie2, which finally gives us the joint velocities to use for our robot. Now, we saw the implementation of our human-in-the-loop controller while the CVFs are active. Note on the video on the left that even when the human is inputted commands that will lose visibility, the CVFs slow down the manipulator to ensure this never happens. The human can also open and close the gripper and activate and deactivate the visual servoing controller to pick and manipulate the block. Lastly, we created a collaborative placing action that follows the same scheme as the picking one with one major difference. Due to the occlusion created by the gripper when handling a block, we allow for an auxiliary robot to provide visual feedback using a similar camera. This feedback is then used to help place the block with precision, which is especially needed when assembling a structure with blocks on top of each other. The pick and place functionality are demonstrated in this final experiment, where a simple 3-block tower is assembled. The robot mobile-based motions and the obstacle avoidance are handled by a sampling-based, bidirectional, asymptotically optimal, fast-marching tree algorithm that computes efficient trajectories and avoids unsafe manipulator singularities. We also remarked the use of the second robot to achieve a high precision on the placing action, as explained before. The final structure is built with precision, relatively fast, and always ensuring object visibility and structural stability, where the latter one is a byproduct of optimizing for jerk and precision in the process. For more details on the theory and implementation, we refer readers to the original paper. If you have any further questions, feel free to contact any of the authors at the following emails. Thank you for listening.